Hello, everybody. I'd like to welcome you to the September 2020 edition of Green Infrastructure, Climate, and Cities. For those of you who are joining us for the first time, this is a monthly seminar series that CC Run puts on with a variety of partners at the first Wednesday of every month. We've been doing these since 2014. We have a variety of speakers. We archive all of our presentations, which are webcasts, so you can watch this live online, and you can also see the ones that we've done in the past. As you know from the registration link, we offer PDH credits to continuing education students. Today's topic is exploring uncertainties in stormwater planning in the era of climate change. And the speakers will be primarily students enrolled in a class offered over this past summer at Drexel University. And they're both university students as well as continuing education students. And these students have been working with 7 different stormwater utilities on this topic. And so today we're co-hosting this presentation with the American Water Resources Association Philadelphia chapter. And our agenda, sorry, I want to also just acknowledge the contributions of Fatima Nasrallah, who is the TA for the class, and Corinne Tangjakul, who has been managing all of the logistical planning and the interactions with the utilities, between the utilities and the students. So our agenda for today is a short 15-minute introduction by me, just to orient you to what you will be seeing. And then we'll go through a series of 10-minute presentations by students who took the class and who will be presenting their work. And I'll talk a little bit more about what that work will be in a moment. We'll cycle through the cities in the order shown here, from Washington, D.C. to Camden, Richmond, Baltimore, Charles County, Frederick, Maryland, Tacoma Park, Maryland. Our logistics for the day, audience members will remain muted throughout the webinar, although you can submit questions at any point through the Q&A function. We'll be typing responses to these questions during the entire seminar today, and we've got actually some scientific experts in this topic who are also among the participants, and they will also be fielding questions. So feel free to interact with us as much as possible through the Q&A link. The chat box is for everything else. If you're having problems hearing the speakers or seeing the slides, any kind of logistical problems, you can use the chat box. And in the interest of time, we cannot take verbal questions this time. I apologize for that, but we have an action-packed presentation. And I just want to also make a note that students you're seeing today, student work. These are not consulting projects. These are not sponsored research projects. This is very much work that was produced in a short amount of time that is really interesting, but it's an exploratory presentation to look at some of these emerging topics in stormwater management and how they can be addressed. So I just want to make that caveat. So by way of introduction, I'll just show this slide from the National Climate Assessment. You're familiar with this information. Historical heavy precipitation is on the increase. And these 4 charts show different NCA4 regions and the percent increase over different historical periods of extreme precipitation, different measures of extreme precipitation. And our region, the Northeast Mid-Atlantic, it has experienced some of the greatest increases in heavy precipitation. And the climate scientists are working on this problem, and we've got lots of global climate models, global circulation models that have been put out there that are being used to look at how these trends may change in the future. And the climate scientists put out charts like this, which, for example, shows projected change in total seasonal precipitation for a particular future time slice. And this is the information that the climate scientists give to the engineers and the stormwater planners. But the stormwater planners and engineers don't always know what to do with this information, because if you have been involved in stormwater management, you realize that your head is usually in problems like this. You're interested in, how is climate change going to change the amount of flow that's moving through our cities and streets? How is it going to change the amount that we're able to capture in our collection systems? how much of it actually bypasses the collection systems and causes flooding in the streets, and what's the impact on vegetated surfaces? How does the projected increase in rainfall intensity compare to the infiltration capacity of the soil? So the goal of this initiative that actually began about 6 months ago with a workshop that CC-RUN put on to investigate the state of the art in applying sort of climate data sets to forward-looking stormwater management policy setting. And if you have not heard of it, we conducted a workshop and a series of webinars called Adapting Stormwater Management for a Changing Climate. And you can download this information. You can see some recordings. But as an outcome of that workshop, a variety of utility partners said that they wanted to take a shot at implementing some of these methods. And so what we did was introduced a new summer course, problem-based learning course for both university and continuing education students, where we investigated a series of questions. So, how should utilities update, amend, and modify their stormwater policies given climate change? Where do we get the data that we need to do this? How uncertain and how variable could that data be? And what factors actually are responsible for that uncertainty and variability? And how do we address those in this field? What's the state of the art? And how different might future storms be, specifically design storms, from those that are based on historical information? So as I said at the intro, we worked with 7 different utilities shown here. It turns out a lot of them were in Maryland, but we started up, the furthest north is Camden and the furthest south is Richmond. And the students went through a rigorous series of activities, beginning with some extensive literature review where we read published articles, peer-reviewed articles on this topic. They conducted interviews. As we know, climate change adaptation requires co-generation. We need the experts working with the stakeholders. So the students conducted interviews of their government partners and used a series of tools. The class was an opportunity to introduce these tools to the students. So we used the Climate Explorer, shown here, to compare historical and future precipitation. And then we use this MACA tool as our main portal for accessing climate projections for each of the study area. And then we access climate data. The students developed a simple statistical approach to adjusting the design storms used in each of these utilities to factor in precipitation. And in a nutshell, what this procedure is you use the climate model output, you look at a historical period, you look at a future period, you look at the percentage change in, for example, precipitation in those 2 periods, and then you come up with a ratio or a percentage change factor, and then you use that change factor and you apply it to to all of the ordinates of a historical design storm. So once they did that, they plugged this into some stormwater modeling, and then they developed some recommendations. So my main point in this introductory presentation, though, is to introduce the fact that this work requires a series of key decisions, and these are not simple decisions that need to be made. And how you make these decisions very much determines where you land in terms of these modifying these historical design storms. And I'll go through these quickly because these are the decisions that the students sort of contemplated all summer, and you're going to hear in their individual presentation how they resolve these questions. So of course we need to select design storms. And so to do that, we looked at local codes, we interviewed the utilities, we looked at other guidance documents. Then for developing the delta change factors, as I mentioned, you need to compare some kind of future period to some kind of historical period, and how you define those periods will change your factors, right? So we decided as a group to use one historical baseline period. So that's historical observations between 71 and 2000. And then we looked at least 3 different future periods, the 2020s, 2050s, and 2080s, with some groups using some other periods that their stakeholders were interested in. Then you need to look at how emissions of greenhouse gases will change in the future. And there are lots of ways of doing this. We picked two emission scenarios. So RCP 4.5, which is a scenario in which we've stabilized emissions by 2100. That's something like 4.5 watts per square meter. So that's sort of an optimistic assessment of what will be. And we also considered 8.5, which is more of a business as usual, where we don't actually reduce emissions significantly. Then we needed to pick among all of the climate models that are out there, which ones we would use. And as you'll see in the presentations, this decision is quite important. Different models give different results. And the data that you use through the models, the downscaled data, there are different techniques for downscaling the data. We're not going to talk today about those techniques, but we needed to pick different techniques. And so what the students did in a nutshell is they picked 10 models that seemed to best represent the historical precipitation. And then they used two different downscaled data products. Again, if you've never heard these words, it's fine. The LIVNA data and the MET data are just two different approaches. And then they computed their delta change factors. And as you'll see, they did it at a monthly time step. And the statistics get really complex. You look at the means, you can look at the medians, you can look at the extremes, you can look at seasonal averages. So they'll tell you how they went through all of this variability. And then they picked a modeling approach. This course was not about hydrologic modeling, so the students relied on modeling skills that they had based on their previous experience and came up with some recommendations. So before I turn it over to the students, I just wanted to orient you a little bit. This is projected changes in annual precipitation across all of the study areas that we considered. So on the left, you see average annual precipitation, the historical, and then going forward, the 2020s, 2050s, and 2080s. And you can see the two different RCPs. So, you see modest increases in annual precipitation. The middle chart is the minimum annual precipitation. So you see that, during drought years, we could be significantly below the averages. And you see some formidable differences by the RCP, for example, in the 2080s. And then to the right is the maximum annual precipitation. And you'll see, also some big differences between the RCPs in certain time slices. And again, these boxes represent across our 7 utilities. So this is just to contextualize the sort of climate context in which these students were working. This is the same kind of a chart, but just showing changes in the number of days with more than 1 inch of precipitation. So, from, something between 5 and 10 on average, but, you could have very little and you could have as much as 25, 30, depending on the scenario. So you begin to see some of the variability that we are dealing with here. The Manka tool that we used gives you the option of choosing between 20 different global climate models and 2 different downscale data sets. And what this complicated chart just shows you are on the left-hand side, the models on the left, the grid on the left is the MET data, the grid on the right is the LIVNA data, and the X's denote the models and the data sets that the different groups chose. And you'll see this is another source of uncertainty in this type of analysis, but there are some clear losers and clear winners. So the Norway model shown in red seemed to come out as a favorite among all the different groups, and the Australian and United Kingdom models were less favored. So this is just another factor. And then the students developed monthly delta change factors, and you see here the 2020s on the left, the 2050s in the middle, the 2080s on the right, and you see some seasonal changes, some differences based on RCPs. And so what we did is sifted through all of this information and ultimately landed on a series of delta change factors here, which I'm not going to talk about anymore. The explanation for how the different groups got to these delta change factors is described on the bottom, but you're going to hear about this as we move on into the individual presentations. So with that introduction, what I'd like to do is stop sharing and hand it over to our first group. So I believe that is Washington, D.C. I will stop sharing. And Washington, D.C., if you could jump in. Great. Take it away.
Thank you. Hi, I'm Kayla, and I'm in a group with Ian and Anna. And our partners for this project was Washington, D.C., specifically the Department of Energy and Environment. And in our early discussions, we found that some of the current stormwater issues are a variety of flooding issues due to intense rainfall events and then inadequate infrastructure to deal with these events. So for our delta change analysis, like Franco said, we worked with the MACA tool to find our 10 global climate models, and we did this by comparing it to Washington, D.C. historical observed data. And once we found those, we pulled data for RCP 4.5 and 8.5, and for the two resolutions of LIVNA and MIT data. And we pulled this for the historical data for 1971 to 2000, and then for our future projection data, which goes to year 2100. And these are the 10 global climate models that we chose. Once we pulled all of this data, we found the monthly averages for the historical model data. And then we also found the monthly averages for each resolution, RCP, and time slice for the projected data that we found for the projected data. And then from all of this data, we used the following equation to calculate our delta change factors. So the next couple of slides are our specific results for the delta change factors. This first one here is for the near term for the 2020s. Some things to point out is that we see a greater variability in October and September as well. This is kind of seen throughout some of the groups, and so it's thought that's possibly due to hurricane season in these areas. And then another thing is that all of the medians are greater than 0. Here's the box plot for our 2050s, or midterm. We're seeing greater variability in the late summer and fall months again. And then compared to the 2020s, we are seeing increasing delta change factors. And then all of our medians, again, are greater than 0. And then finally, here's our 2080s result. Compared to the 2020s and the 2050s, we are seeing greater variability. And this is thought to be due to the 2080s are further away from the present time, so making it more difficult to project that data, or to predict that data. Again, all of our medians are greater than 0. And then compared to the 2020s and the 2050s, we are still seeing a projected or an increasing trend in our delta change factors. So the delta change, so from all of this data, we chose 6 different variables to use for our modeling. And we chose these for the time slices of 2050s and the 2080s. And this was chosen because since we're currently in the 2020s, we wanted to focus specifically on our projected data. And we decided to use the minimum, maximum, and average median delta change factors. And these were chosen based on the fact that they're more likely to occur and then more likely to be taken seriously.
So in order to make these DCFs more tangible, we created a case study. So the DOE oversees stormwater regulation at a variety of development sites around the city. And this is the residential site that the DOE provided us. So this site previously had a 2-story home, but now after development, it was raised to be a 3-story house. And with the change of land cover and the changing hydrology of the site, the certain stormwater infrastructure had to be installed to compensate for this. So our modeling approach, so we decided to use HydroCAD to conduct the site analysis. And we did this because the DOE provided a number of variables in their engineering plans that can be easily input into this program. So one thing to note too is that HydroCAD uses TR55 and TR20 for calculating the runoff. And as you can see, this model has three main components. So first there's the subcatchment, there's one infiltration trench, which is the BMP, which is best management practice, and a point of interest. And at the point of interest is where we analyze the volume and the rates for the stormwater flows. So the site stormwater model inputs. So the inputs were included in the the inputs that were included in the model were pulled from the engineering design that was provided to us. So these include subcatchment properties, infiltration trench design details, and the infiltration rate for the given design plans. So the subcatchment properties include information about soil and land cover, and this can be seen on the figure on the left. And the best management practice or the infiltration trench design details for the site can be seen on the right.
Okay, so then we had to choose which design storms we were going to look at in the model. So we looked at the DC stormwater management guidance to see that they require analysis of the 2-year, the 15-year, and the 100-year 24-hour storms. And for those storms, we use the NRCS Type 2 distribution. And so I know this chart is a lot of data. I'm just going to point a couple things out quickly. For the historical data, so we chose a 2-year historical, a 15-year historical, and a 100-year historical rainfall value. And so we chose those from NOAA Atlas 14 to use as our, I guess, baseline condition. And so then what we did was we applied all of those 6 DCF values, which Kayla talked about a couple slides earlier, to that baseline value, and then reran the model to see what our results were. And so this kind of just shows what we're looking at, and specifically we're looking at the BMP outflow in inches, so that's the volume that we're analyzing, and then the peak BMP outflow is our peak rate that we're analyzing for stormwater compliance. And so, oh, actually, Kayla, could you go back one slide? One thing that I do want to point out quickly is that in the 2-year storms, we're not seeing any runoff. And I'll get to the reason behind that a little bit later. But just for reference, we did not do any more, I guess, statistics for that 2-year storm. So go ahead. Yep. So these statistics, so what you're seeing here is the change in site runoff. And we did this in inches so that we could compare it directly to the rainfall. And so what you're seeing here in this chart is the rainfall that we used for the input to the model, and in parentheses is the delta change factor. And so what you're seeing under the runoff column is the runoff in inches and the percent change to the runoff in the baseline condition model. So what you may notice is that they're not equal. And so, you know, in some cases we're seeing a delta change factor of 12.6 for the 15-year storm in the max, but we're actually seeing an increase in runoff of 51%. And so we only pull these charts for the 2080s because there is a higher variability in our data, just to not, I guess, bore you guys. So go ahead to the next slide. So we also looked, like I said, at the peak rates on the outflow from our site. And so you can see it's sort of the same trend where our rate is not, the increase in rate is not equal to the increase in rainfall. Next slide. So I guess what does that all mean? So what we wanted to look at was other people who have looked at studies similar to this and developed their own delta change factors to see, I guess, how our results compared to theirs. And so here we're seeing, so in the first two columns, it's what we found. And then the third column is a paper published by Mark Maimoni, who found, those values. And then we also compared to the EPA stormwater management model climate adjuster tool. And so what we're seeing here basically is that our values are in the range of what other studies have found. While some may have more variability, like the swim cat model for the very far term has a pretty large variability, but we are, within those values. And so I guess what we want to talk about as far as the modeling implications and how is this applicable to stormwater designers. So the BMP, as I mentioned in that slide earlier, that there was still no runoff from the 2-year storm. And I believe this is due to the BMP being designed for static storage as opposed to being run through a dynamic model, which is definitely a topic for a whole nother presentation. But we did see a significant increase in runoff volumes and rates in, I guess, in the model, even though we only had maybe a storm increase of, our delta change factor of 10 or 12%, which you can see at the bottom, we were seeing runoff rates and peak rates that were much higher than that. So what we would suggest and recommend is to use those, maximum medium values because they are more realistic and, conservative for future stormwater design in this area. And so I know that was a lot, so I'm kind of expecting a lot of questions. So we'll open it up to anyone here.
Actually, we're opening it up to to DC themselves to react and ask questions. So James or Julianne, do you have anything you'd like to ask? Otherwise, we can take one question from the general group.
I admit I'll need a little bit to digest that real quick.
Absolutely understandable. Do any of our other scientific experts want to weigh in any way? Let's check if if there's any questions, Q&A. Okay. I will say though that this question about why the runoff volumes are greater than the precipitation, or the increases in runoff are greater than the increases in precipitation. I think you'll see this comes up in multiple modeling efforts, and it is quite interesting and actually a little bit alarming. Did the group want to just say anything more about the justification that you came up with for that?
I believe it was due to the initial abstractions, and as the initial abstractions are still the same no matter what storm I guess you're looking at, right? And so as there's more rainfall on top of that, you may see the larger increase in runoff volume and rates. I believe that's our justification for that. I know Greg had more to say about that as well, who's another group in this class.
Right. And so we'll hear more about that going forward. But I mean, I think it's an interesting discussion point also because part of it could be a physical reality, right? It could be that once you saturate the soil, that it's essentially impervious, and that's what you're talking about in terms of the abstractions. But there's also assumptions behind the models, and this model based on TR55 has a constant initial abstraction, a constant amount of water that's required before you initiate runoff. And so some of these outcomes that we'll be talking about today could be a function of the modeling, which is, I think, another interesting insight that we got from this exercise. All right, so I think we'll move on. Thank you, Washington, D.C. Let's move on to Marissa. You can pull up Camden.
All right.
And Marissa and I are going to do a tag team on this because Marissa used a model that a master's student of mine had developed on another project. So I'll jump in a second, but take it away, Marissa.
All right. Hello, everyone. So I got to work with Camden County and their Municipal Utilities Authority for this project. Specifically, I got in contact with Scott and Tim, and they were great with giving us the location that we needed and some details. So our study area, we focused on the combined sewer shed that was located upstream of the Creamer Hill neighborhood, and that's located in Northwest Camden. And this area is the most flood-prone neighborhood, and it is also home to CS32, which is the largest CSO in, or that CCMUI works with in Camden. So when it came to the selection of global climate models, we first focused on the RCP 4.5 metadata set results only. And then from there, we picked the 10 best models that represented the historical precipitation data that we collected. With that, we then applied those down to the RCP 4.5 LIVNA, and then the RCP 8.5 Meta and RCP 8.5 LIVNA as well. And that was a way for us to kind of keep a consistency with the data that we were working with. And it resulted in these 10 models that we decided to work with to find our delta change factors. Once we had the delta change factors, we ran into the problem of having a lot and not sure where to go when to settle down and have a few values to work with. So by using the Atlas 14 seasonality analysis that they provided, it gave us this table that let us see the fact that July, August, and September have the highest chance of exceeding the annual precipitation amount. And that is for all of this type of storms that can occur that you can see on the right, such as the 2-year storm, 5-year storm, and so forth. So with those 3 months, we then had to break it down to get a little bit more values to work with. So we first split our data up by each type of RCP, and then we averaged the data based off all those months. So on the image that you can see on the right, at top, we have all of our RCP data, and then the lines represent how they were averaged down. So we average, as you can see with the red line, we average the July values for the 4.5 Meta and so forth with each month and RCP. And then once we had those average monthly values, it was decided to put all of the RCP values together by month to get a single January, August, and September value. So that led us to have 3 RCPs for the 50s time slice that we focused on, and then 3 for the 80s time slice. And then here is the table representing all 6 DCF values that we chose. As you can see, the 2080 September value ended up being very, very low compared to what I expected to be a little bit higher, because values not including the 80s ranged from 10 to 25%. And then July gave us an overall least amount of variability, and then August ended up being intermediate.
So we modeled the Creamer Hill neighborhood in PC Swim. And as I mentioned, this was a model that we had developed previously working with CCMUA, and another master's student, Joseph McGovern, developed. So we used PC Swim. We modeled the combined sewer shed. So what's unique, I think, about this modeling project is that this was a combined sewer. So we had sanitary base flow in the system. The model also had tidal boundary conditions because the CS32 discharges into a tidal portion of the Delaware River. And because the model is used for a continuous simulation as well, we also had evaporation built in. I'll mention that the model was calibrated and validated in consultation with CCMUA and their consultant, CDM Smith. And so we had synchronized this model and made sure that it was reasonable compared to the service area wide model that they're using. Can you go to the next slide? So here's just an image of the model. So we have much coarser resolution in the green areas. That was just because we wanted to get the overall contributions from those upstream areas in there. But the red area, if you go to the next slide, was represented with higher resolution, because another, not part of this project, but another initiative here is to look at how green infrastructure can attenuate some of these increases in precipitation. But there you can see CS32. And if you go to the next slide, what we did was took the historical 24-hour precipitation amounts for the 2-year, 10-year, and 100-year storms. We assumed a type 2 distribution. We applied the 6 different DCFs that Marissa mentioned. And then what we reported was the total volume of CSO discharge per storm at that outfall location. And then a complement to that was we looked at the water balance within the entire model domain to see, to sort of give us some insight into where the precipitation, what was the fate of the precipitation that was being applied. Go ahead, next slide. So this chart shows you on the horizontal axis, the total event precipitation. The vertical axis is the total CSO discharge volume in millions of gallons. And then the three, you see the 2-year, the 10-year, and the 100-year storms, and each of the dots is a different delta change factor applied there. So a few things of note, the worst case future 2-year storm still causes less CSO than today's 10-year storm. So now that might not be the case if we were looking at the 5-year storm, but in this case, just comparing the 2 to the 10, and similarly, the worst case scenario for the 10-year storm is still below today's 100-year storm in terms of CSO volume. The other thing that we see is that the higher the DCF, so in other words, the further you move to the right within any of those storms, any of those return periods, the more you move to the right, the more CSO discharge you get, which is to be expected. You've got more precipitation. But we started to ask ourselves, is the increase in CSO discharge equivalent to the increase in precipitation, similar to the discussion that the previous group did? So if you go to the next slide, here we're showing the maximum computed percent increase. So looking at the baseline and then comparing it to the 21% increase in event precipitation. That's the worst case delta change factor. And then you see the 3 bars are the percent increase. So for the 2-year, well, let me just say that horizontal line is the increase in precipitation. So it's about a 21%. And similar to the previous group, what we see is that the increase in CSO discharge is above that 21%. And additionally, that increase is greatest for the smaller storm, the 2-year storm, and lesser for the 100 storm. So percentage-wise, the climate change seems to have a bigger impact on the smaller storms. And we think that's because there's a lot of, today's 100-year storm already saturates the surface. So if you go to the next slide, what we have here are some pie charts that show the water balance. So first, the baseline conditions. So on the left, and you got the 2-year, the 10-year, and the 100-year. What you see, each of the different sort of slices of the pie are different components of the water budget. So the first finding is that whether you're looking at baseline or worst case, evaporation and storage are insignificant components of the water balance. So the bulk of the precipitation is ending up either as runoff or as infiltration. And surface runoff is a larger percentage of the larger storms than the infiltration. So, if you look at the baseline and go down, you see the gray fraction is getting bigger. And then if you look from left to right in any of the rows, you see that the gray portion is getting bigger. So the increase in precipitation is causing an increase in runoff, and the next, if you can click on the next bullet, and a reduction in percentage-wise. There could be an increase in the overall amount of infiltration, but percentage-wise, as a percentage of the precipitation applied, that percentage is going down. So from that percentage-wise, climate change seems like will have a more pronounced impact on the water balance of the smaller events. Go to the next slide.
So
Go
in,
ahead, Melissa.
in conclusion, our DCF selection process provided a range, and more importantly, the focus on were the intermediate values relating to August.
And then the today's 2-year, 10-year, and 100-year 24-hour storms already caused the system to overflow, but more rain in the future is going to cause a larger volume. But at least for this sewer system, with the conveyance capacity and land use as they are, the climate change will have a greater proportion on the water balance for the more frequently occurring lower return period storms. And we think that's because today's big storms already surcharge the system. But as I mentioned, an interesting place to go here would be to now institute some stormwater controls and see how much of these increases could be in CSO discharge could be attenuated through green infrastructures, through some of these cloudburst strategies that store water in the streets, et cetera. So with that, we will ask if Scott or Tim from CCMUA want to make any questions or comments.
Thanks, Franco. This is Scott Schreiber. First of all, I could just say that, the future is bright. There's a lot of smart students and people that are talking about really amazing things that are quite frankly over my head. But I'm appreciative of the fact of this group is working on these things. And so thank you. It makes me feel better about where we are in the world. That's first and foremost. Second of all, this is hugely helpful to us. We're about to hopefully embark on a huge green infrastructure project, something that will last 10 or 15 years to capture as much flow as possible in the city of Camden. And to look out now and be able to look out into the future and understand what impact that green infrastructure may have, and what, more importantly, what we can do to make this green infrastructure more resilient or larger or more capable of handling flow for that future. It'll make sure that our investment is not lost because of higher intensity storms or because of climate change. And so, I think there's a real place for this work and this science in how we plan and move to the future, because we're at the perfect time where these calculations and planning and design are all going to be kind of needed at the same time. So I think we should talk, Franco, offline about how we can look at this in a more robust way and in a larger way across the city. But overall, I just want to say thank you, and again, appreciative of how smart the group is that can work through these issues.
Thanks, Scott.
Yeah, thank you.
Any other, we've got about 2 minutes if there's any other questions.
Hey, Franco, can you hear me?
Yep.
Oh, there's a double muting system. Sorry about that. Some things that stood out to me was how the difference between the rosy scenario and the apocalyptic scenario are not terribly different. So, I mean, what that says to me is that people don't have, if people don't want to plan for the worst case scenario, learning from this, I would say, look, it doesn't have to be the worst case scenario. Even the rosy scenario is going to cause some, significant increases. And I like the way that you guys sort of structured your analysis for a couple of reasons, because the way that it's our long-term control plan is going to work is that that CSO rapid treatment or dealing with the overflows there through some gray infrastructure is last in our plan, not first. So it is completely appropriate, not only appropriate, but completely essential to be looking at 2050, sort of time range, because that coincides with when we're going to be addressing that specific issue. So yeah, I think you guys sort of structured your analysis in a very helpful way for us.
That's great. Thanks, Tim. And I'll just say also, you know, the models, of course, produce all kinds of things, and we just elected to look at the water balance and the CSO volumes. But you know, it would be useful probably to look at flood depths and to see if you know, because it could be that certain things that don't look as bad as you might have expected in terms of volumes of CSO look horrific in terms of depth of ponding, for example. So there's a lot we can get out of these tools, and I guess more coming. So thanks. Let's move on to, thanks Marissa, you can stop sharing. Richmond, you guys are up. And while we're transitioning, there's a lot of interesting conversation happening in the Q&A, so feel free to jump in, any of our technical experts. Go ahead.
Sure. So our group is the City of Richmond, and I worked with Julia and Jake. So I'll pass it over to Julia.
Hi, I'm Julia. So the Richmond, Virginia group worked with Brianne Mullen and Jen Clark from the Office of Sustainability and the Stormwater Utility Departments. We met and discussed some of the issues that Richmond has been facing regarding extreme events and compiled a list of the general issues in Richmond regarding stormwater. So a third of Richmond contributes to a combined sewer overflow, but on days where there isn't an overflow event, they have 2/3 of the city that is only stormwater drainage. Anything that goes through the treatment plant is handled by the wastewater department, and there's a lot of interplay between the two sides of water management in the city. And an important aspect of the city is the unique flood wall, built to withstand a 280-year storm. We've included some information about the city's initiatives in preventing flooding within the city, including the aforementioned wall and the levees within the city. So with the basic information about the city's layout in hand, and following several weeks of discussion on how to best prepare helpful information for our partners, the Richmond group developed a set of models to best describe the historical rain data. 10 models from both the MET data and the LIVNA data were selected by comparing the baseline period of historical rain data to the models data to determine which combination of the models best approximated the observed data. The highlighted models on the right are the ones that we selected. For selecting our DCF factors, we downloaded the projected monthly precipitation data for the time slices we selected and averaged all of the Januaries, Februaries, and so on for each time slice for each of our selected models to come up with a monthly average precipitation for each model and for each time slice. We then used these values and compared them to the observed data using the formula below to approximately multiply the current precipitation by the calculated change factor. Using a box and whisker plot, we displayed these calculated factors for each time slice to get an overall picture of each month for each time slice. We included the 3 time slices similar to the other groups and included the mean DCF for each month for convenience. But this was a lot of data that ultimately had to be parsed down for the purposes of design and aiding our municipality in seeing how the future precipitation would change. You can go to the next slide. So we've included the 2020s, which has also been included in the other groups. We have the 2030s and the 2070s also included, even though these are also included in the 2020s and 2080s respectively. Those two only cover 10 years, and those were requested by our municipality partners specifically. But we included them as well, and we were happy to provide the municipality with those.
Okay, so to select the DCFs, we decided to use the seasonal numbers we calculated using both RCP 4.5 and RCP 8.5. So we chose the winter months because the DCF had the highest increase, the fall had the least increase, and the spring had the greatest variation between the 2050s and 2080s. And all the values show an increase in precipitation. So once again, here's our delta change factor plots. And we provided the lines for each DCF we chose, so you can see it sort of lines up with the lowest average and the highest average values, and it's the 2080s values. So for the design storms, we used the historical depths of the 2U, which are smaller, more frequent storms, 10U, which is in the Richmond design standards, and the 100E, because it's a larger storm, and the two charts, so the 2050s changes and the 2080s changes, the historical on top, and then the site, and then the highest ones. So the site we chose was a city block bounded by Main Street, Carey Street, 25th and 26th. And there were two large apartment buildings. One was recently constructed. So we have some numbers on the site area, the impervious area and pervious area. So it was modeled in HydroCAD.
Thanks, guys. And moving forward our results, we kind of have subsequent slides of 2050s and 2080s. And I mean, it almost seems kind of obvious that, you know, as rainfall increases, your volume is going to increase. And as your rainfall increases, you would expect your peak rates to also increase. But these charts can give you a sense of, you know, the relative increase. So if you look at the chart all the way to the left, that's just the rainfall depths. The first bar is the historical bar. And then you can see that we basically applied the delta change factors, which are just percent increases over that historical storm. If you take that chart and kind of keep that in mind while you look at the volume and the rates of runoff, you can see the patterns are very similar. Similarly with the 2080s, you start to see all the bars kind of shift up a little bit, but the general results are very similar. You know, it's really what you would expect. Moving on to something that both groups have talked about is that, you know, something we found really interesting is that with the change of precipitation did not correlate to the same change in runoff volume or the same change in runoff rate. And so what these charts show, both of these are for the 2050s. I've dashed in a line where, so for instance, the 11.3%, we increased the precipitation by 11.3%. However, you can see that the response is always much higher. And surprisingly too, is that they're nonlinear. What I find even more interesting is that, you know, we were using a very simple HydroCAD model. We didn't have a lot of information about drainage infrastructure, where the stuff was going. We made some really basic assumptions, and we essentially got the same type of response that the Camden group got. And they're using a more sophisticated model with a lot more input. Again, you see the 2-year storm has the largest difference. And so that would, you know, lead you to believe that maybe we should be more careful about our smaller storms and put more attention toward those since they have the greatest impact based on our modeling results. You see similar results in the 2080s. Again, you see these nonlinear responses with the greatest changes actually occurring in the 2-year storms. And finally, we put together, you know, a slide of discussions and recommendations. And I think as we go through all of this, it's really important to, you know, remember that these box plots, they have a lot of information in them. It's a range of values, and we selected 6 of these values among thousands. So it's going to be really important to take into account that variability and the uncertainty in these projections, and try to figure out for a municipality, you know, what is reasonable and what is adequate to undertake. It's also important to take a look at your time horizon. You know, a lot of times we have 50-year infrastructure or 100-year infrastructure. And so you have to kind of take that into account because the further projections are more variable and the means and the medians are much higher. That being said, you know, it's clear, you know, across the board before this class, during this class, that, you know, precipitation in our region is increasing. And it's important that we start making policy changes to address the fact that we are going to be seeing precipitation increases. This could be, you know, changes in policies to managing small storms, managing static storage volume, like the first group discussed in their BMP. Also looking at just different stormwater management thresholds, especially since we saw that the smaller storms were had a different response. We also found it interesting, you know, I think in the beginning of these courses, as we were interviewing our municipalities, just understanding that, you know, a lot of these municipalities have this huge task on their hands, and there's not always a lot of funding. So it's important to advocate for that funding to make sure that people have the available resources, that they can identify the vulnerable infrastructure and, you know, adapt with their assets that they currently have and the ones that they'll be building soon. And continuing public outreach and educational efforts on climate change impacts with your communities. And with that, we'll open it up to both Brianne and Jen for questions.
Hey, this is Brianne. Thank you guys so much. I'll echo what some of the previous clients from other cities said, which is that this is amazing work and we really appreciate it. I also want to thank you for being willing to do some customization with the date ranges. We are doing this at the same time as we're doing a more comprehensive climate vulnerability and risk assessment. And so it's really helpful to have the time horizons that we're looking at precipitation be similar to those that we're looking at for heat, so that we can start to paint a more comprehensive picture of what climate change might be doing to our community in the future. I did have a quick question. Jake, you were talking about in choosing DCFs, and I apologize, I am not a scientist in any way, but you mentioned, yeah, this slide, you mentioned that you chose, there was some sort of process of choosing the winter seasonal DCF because it had the highest value, and I wondered if one of you could explain that a little bit more.
Sure. So we basically took all of our winters and then we averaged them out across. So we took like our DCFs for December, January, and February, and we averaged them. We took the DCFs for March, April, May, and averaged those. And so we ended up with basically these seasonal averages. And then in looking at them, we wanted to provide a range of you know, potential outcomes when we were doing our modeling exercise. And so we decided to choose the winter because it had the highest average value, and the fall since it had the lowest, and then the spring just because the 3.8 and the 5.9, you know, we're a little bit further apart than the 4.6 and the 5.1. So that was pretty arbitrary.
Got it. Okay, thank you.
Yeah, that being said, like thousands of DCFs went into this, so it should just be taken with a grain of salt that we chose 6 using this method.
Right. And then the other thing I'll just say is that the slide that you had on the, you know, what inches of increase in rainfall could potentially translate to in terms of runoff volume is really helpful too, because I think sometimes when we're working with, you know, the engineers and other folks in our utilities, they might see, you know, I don't know, 1 inch increase per year or sorry, by like mid-century, something like that. And that doesn't mean a lot to them, but seeing some of these volumes and runoff numbers, I think will be helpful to translate like what that could potentially mean in the future. So thank you guys so much. That's all I have.
Thanks so much. And I just want to, you know, underscore as we transition over to the next group, which is Baltimore. Great job going through and presenting all of the variability. That's been the name of the game in this class. I perhaps naively thought that we would sift through all these methods and come up with an optimal strategy for defining the ranges that we should use for these delta change factors. But there is a lot of subjectivity in where you land in the full range of possible futures, and I think that's just really important thing to realize as utilities and others move forward in this, is that there will be, there does need to be some kind of a stakeholder-driven process where the uncertainty is discussed among the stakeholders who are impacted, and whether, as Tim suggested earlier, you shoot for something that's on the lower end of what the future could be, but will have, you're fairly confident will occur and you'll get a benefit, or whether you shoot for the sort of more drastic range, end of the range. And so I just think sifting through this uncertainty is just the name of the game. So with that, I'll be quiet and move on to Baltimore.
Okay, Baltimore, I hope this is, our slides should be up on the screen. I hope you can see them, and Caroline will start us off.
Hello, my name is Caroline Houlihan. My collaborators from Drexel are Sean Flynn and Ryan Quinn. We worked with Kimberly Grove and Jamil Yusuf of Baltimore City Department of Public Works. Baltimore City is a subsection of Baltimore County, Maryland, outlined in black here. Baltimore has experienced destructive microstorms, which have caused the flooding of local streams, impacted road drainage, and prompted evacuations. Baltimore is vulnerable to the effects of both sea level rise and coastal storms, and will need to adapt as the climate changes. In order to do this, Baltimore will have to take on two essential tasks: securing funding and collaborating with other agencies. Funding to conduct studies related to climate change impact is a key element to communicate and justify additional funding for stormwater management improvements. Stormwater management improvements for climate change adaptation will not be realized without the cooperation and support from agencies such as the Baltimore Department of Transportation, whose infrastructure and design requirements are of critical consideration to stormwater. In order to create delta change factors using 10 models, they had to be picked from the 20 available. We chose to rank the models by their bias, meaning that the 10 models whose historical values have the smallest % difference from the historical observed precipitation are chosen for continued analysis. The bias for the met data and LINVA grid cells are averaged for each model. So we produced DCFs for 10 models, 2 downscaling methods, 2 RCPs, and 3 time slices with 12 months each, which comes to 1,440 DCFs. This box and whisker plot helps us to notice trends in season and time slice. DCFs for the summer and winter seasons show a large increase in precipitation, more so than other seasons. Precipitation increases and precipitation extremes also become greater as you move from the 2020s time slice to the 2080s time slice.
Hello, this is Sean, and in leaving off where Caroline did with the results that we had to take those almost 1,500 DCFs and try to make sense of them and boil them down into something that was palatable so we can apply it to a case study and have them be understandable. So the first thing we wanted to do in that process was look at our results and notice some things. So on the screen here, we have a little snip from that previous box and whisker. And the one thing we saw immediately was the seasonal variation. So grouping by season seems to be a pretty logical way to group these almost 2,000 numbers. And another thing we saw was that there was no apparent variation by downscaling data set. So we weren't going to isolate by data set. Moving forward to how we simplified our DCFs into less of them. We, again, have the meteorological season, and we also, through just a co-generation of ideas with our utility, we decided to go with a design life of 100 years, which is most of the conveyance infrastructure and how long we want to keep things around. And looking at the future time slices and the seasons, we saw that winter had the greatest increases. And essentially we came up with these 24 DCFs instead of 1440, and we can look at these by time slice, season, and then we did separate by the climate projection or climate trajectory, the RCP values of 4.5 and 8.5. So we end up with these 24 values here, selecting really these four for our case study. So this was the process we went through to try and end up with just a few DCFs to consider when moving forward with what can we do with this information. So moving on to our case study, the Baltimore Department of Public Works provided us with 2 different areas that are part of the Watershed 263 Stormwater Demonstration Project. It's really a planning effort that includes 930 acres, and it's really a revitalization project that utilizes the application of urban forestry watershed projects. So these are 2 of the catchment areas from that, catchment F and catchment O, and they're about 40 acres in southwest Philadelphia, Baltimore. And they're a majority residential, with catchment O being more densely residential and catchment F having a little more green space or less impervious area. The case study was using the 5, 10-year, and 50-year 24-hour duration storm events, and that's in line with the Baltimore City Department of Public Works design standards. So this is something that we can relate to with current design methods. And we also used, like many other groups, HydroCAD, which utilizes TR20 SCS unit hydrograph calculations. And here's just some notes about what we input into our model. So we did use an NRCS type 2 distribution. We collected hydraulic soil group information about each catchment area, and we assigned curve numbers, which are summarized in this table here. So this is basically the information that went into our HydroCAD model, and along with these precipitation depths, which, as described by Franco and previous groups, we took NOAA Atlas 14 historical precipitation depths for the 5, 10, and 50-year events, and we applied to each of these single event storm durations. We applied our 4 DCFs and increased the historical number for 2080 winter and each RCP value. And we end up with these precipitation depths or these storm events to run in our model. Probably the biggest takeaway from this is that the 5-year 2080 winter for RCP 8.5 catches up to the 10-year historical NOAA Atlas 14 value. So this is something where we can see, a future 5-year storm is becoming the current design 10-year storm. And the model results essentially reflect that as well, where we can see that this is for catchment F, and this would be peak rate results and then volume results here. And without getting caught up in the numbers too much, we can see that the 5-year 2080 winter RCP 8.5 value is pretty much in line with the historic 10-year. And it's essentially the same reflection in the volume results. these are, again, just, this is for catchment O, and it's essentially the same story here. And I think Ryan will be going into more of an expansion on the study overall and our results.
Thank you, Sean. So this is the part of our presentation where we would like to share aspects of the analysis that surprised us and we thought were worthy of additional discussion. So the first one, when the GCM models were being selected to minimize the bias, we also identified that there's significant existing variability in the historical rainfall record that was interesting to us. So this includes not just the annual year-to-year variability, but also station-to-station variability that you get when you select a rain gauge to base your historical record on. So the overall class is relying on the Climate Explorer data, which is shown on this graph as blue dots. And what we did was just to take a look at the BWI, the Baltimore International Airport rain gauge, which is proximate to Baltimore City, but is actually outside of Baltimore County. So where the Climate Explorer data is based on interpolating rain gauge records and kind of distilling it to a countywide Baltimore County value, BWI is a specific rain gauge. And so I think this graph helps illustrate that there is variability station to station. We will go to the next slide. And when we look at the differences between the two, we see a consistent pattern that the Climate Explorer data historical record has greater annual rainfall than the historical record at BWI. And so there's a difference of about 4.5 inches in the total annual average, but you can see that the actuals range from being rather small to rather large, up to 10, 11, 12 inches in certain years. And we think that this is potentially because of the influence of coastal storms in the historical record that may be large events that have a lot of spatial variability. And so we did go with the approach to minimize the model bias, but we think it's important to understand the underlying historical record and what variability has been seen in the past. The next slide. Sean, you want to go to the next slide?
I did go to the next slide.
Oh, you did go to the next slide, yeah. Oh, yeah, sorry. And so what we did in selecting the model bias is just our GCM averages actually fall in between the Climate Explorer rain gauge data and the BWI observed. And so when we are minimizing the bias, we wound up selecting the GCMs with the highest annual average, but if we had went with BWI, we would have selected the ones with the least. But in the end, that difference only winds up being a few percentages. So we think based on existing literature that the impact on the DCFs is likely to be minimal, but it'd be worth looking at. You go to the next slide.
Sorry, we should probably wrap up and move to the...
Yep. We just have 2 more slides. So real quick, this just echoes what Sean was saying with the 10-year event, historical tenure being equivalent to the 2080 5-year events. We think that this is just a justification for additional stormwater management and investment and the work that was being already initiated by BC DPW. You go to the next slide. And to wrap up, the challenges that BC DPW faces in implementing their regulatory requirements, they also have unfunded mandates, and they know that there's challenges with managing these large events. And so this future climate analysis can be a justification for funders to invest in that sort of planning, and BC DPW has already started to take steps for more detailed additional modeling of their stormwater system, which I think will be interesting to apply these future climate scenarios to.
Great, thank you. Any comments from Kimberly or Jamil?
Hi, yes, this is Kim. I just want to say great presentation by Caroline, Sean, and Ryan. I've really enjoyed working with them. One thing that I appreciated is that you looked at it from a seasonal approach. One question that I have is when you ran your models, did you account for the condition of the trees and the green spaces? They'll be in a dormant state during the winter time. And so was that a consideration when you were running your models? And this is a larger thing to think about in seeing these increases happening during the winter time, which will be a dormant season, how we may be getting a little too dependent on green infrastructure, and it may not be as effective when the increases are happening during that dormant period.
So the model itself does not take into account that, but that is an interesting point. Essentially, we made some generalizations about the overall 40-acre area and described them in this way. We made a cover description. So maybe it would be, there would be ways to adjust this to account for this sort of dormant vegetation or dormant cover effectiveness that you're talking about. I think that's a really interesting point.
And I'll just say there are approaches for modifying curve numbers based on antecedent conditions, based on which would vary as a function of season, and differences in land use, quote unquote land use, meaning vegetation cover. So there are ways of doing this, but I think Kim, your question goes right to the heart of, that another source of uncertainty is the modeling tools that we are using and the capabilities that those modeling tools have to represent what we know, is the actual condition on the ground.
All right, thank you very much. This was a good presentation.
Great, thank you, Baltimore. Unfortunately, we have to move on. So let's go to Charles County. And those of you who have not had a chance to ask your questions, please do. The Q&A has been active, but there's no open questions right now. So please do feel free to ask your questions there.
Ask questions.
All right. Hello, can folks hear me?
Go ahead.
All right. So I'm Hayden Smith. My teammates were Melody Wu and Greg Hoffman, and we were looking at Charles County and wanted to thank Mr. Randy Crowder, who's the stormwater engineer in Charles County and our point of contact. So just for some background, Charles County's location, it's part of the greater DC metropolitan area, on the southern end of Maryland, on the Potomac River. It's a growing county. The population is approaching about 150,000. It's got a municipal separate storm sewer system that's been NPDES permit regulated since 1997. And in the northern part of the county, the largest urban area is Waldorf, Maryland. In these pictures, we see some flash flooding that occurred in the county last summer. And we just included this as an example of some of the extreme precipitation events that have occurred in the area recently that have kind of brought to the attention of a lot of folks the need to consider extreme precipitation and what that might look like in the future.
Right, so we generated our delta change factors pretty similarly to a lot of other groups. So our methodology basically was looking at 20 different GCMs from the 2 different gridded data sets, so the 20 metadata and the 20 LIVNA, and comparing those modeled historical data to the actual historical observed data, we narrowed it down to the 10 best overall GCMs, which turned out to be 6 metadata models and 4 LIVNA. After that, we averaged all of the monthly data for all time slices and used the percent change equation, which is seen on the left, to find our delta change factors. Those came out to be a total of 720 total between the 3 time slices, between 2 RCPs and all the models. Okay, next slide. Okay, so again, we have 240 total DCFs for each time slice, but we plotted them in a box plot so we could like see them better. And as you can see in the 2020 time slice, we kind of we put the 2020 data out of this presentation because we didn't end up using it in our final analysis and modeling. So here we're just looking at the 2050s time range DCFs, and we can see a lot of variability between all the months, between all the DCFs, and also from the 2 RCPs. One concern we had about this was that you really can't tell the difference that RCP plays in getting our DCFs. So we were expecting to see a clear distinction that 8.5 RCP has a lot greater delta change factors, but we didn't see that. We also didn't really see a lot of seasonality in the 2050s. Next slide. Okay, so this is our 2080s delta change factors. We also see a lot of variability, not a clear seasonality, and again, it's really unclear what impact the 2 different RCPs have on the DCFs. We also see some negative medians here in March and in October, so that kind of confuses us a little because we couldn't get a clear picture of what our delta change factors would actually look like in affecting the future rainfall. Next slide. Okay, so when we wanted to narrow down our delta change factors to something a little more workable, so we ended up narrowing it down to 4 total delta change factors. In our pursuit of this, we kept the 2050s and 2080s time ranges as we did before, and we also wanted to keep the RCPs separate so we can clearly tell what impact they have on the delta change factors. When we were talking with our government party member, Randy Crowder, we were saying that seasonality isn't really clear and that, Charles County isn't specifically interested in looking at seasonal patterns. So because of that, and to make the data a little less muddled, we found DCFs by looking at the total annual rainfall and using the median of those instead of monthly. So next slide. So that's how we got to our 4 final DCFs, which are shown on the tables to the top right. So again, these are total annual rainfalls for the 2 time slices at the 2 different RCPs. As you can see, it's a lot more clear than in the monthly data, what effect the RCPs have and how big a difference there is between 2050s and later in 2080, what the DCFs are. So we thought that would be a lot more clear, and those are the 4 DCFs we end up using in our final modeling.
All right, on to the model. We started with our design storms using the 1-year, 2-year, 10-year, and 100-year. And as the other groups did, we used NOAA Atlas 14 to get our existing data. The various storm depths are in the table below. Next slide, please. And then for the site we modeled, we were looking at the Waldorf Urban Redevelopment Corridor. This is an area, a heavily developed area in Charles County, mainly commercial development. And it's bounded by US 301 on the west side, or sorry, the northwest, and a railroad track to the southeast. Given how flat the area is and these major transportation corridors, it makes drainage difficult in the area. Next slide, please. That whole area is about 200 acres. We focused our model on the southern portion of it, a 65 acre area. Had to make a few assumptions on it because we didn't have a lot of detail on drainage patterns here, but we assumed this 65 acre area drained to one location, a forested wetland in the southeast. The pink line on here is our approximation of the longest flow path that we use to determine time of concentration. Next slide. Oh, I think we missed a slide. Can you go back one? There we go. These are our model inputs. The most important is on the right, the delta change factors that we used. We modeled both existing conditions and then 2050 low emissions and high emissions, and 2080 low emissions and high emissions. Next slide. And the results. Existing conditions, the model projected runoff of 138 CFS. Then all of the projected conditions in 2050 and 2080, the runoff ranged from 151 to 157 CFS. So, you know, not as high as I expected, I suppose, but a significant increase over existing conditions. Next slide. We did run, the graph I showed was just for the 2-year storm, and but we also ran the same for the 1-year, 10-year, and so on with similar changes. Next slide. Moving quickly to the conclusions, because that's my favorite part. Some of our top conclusions, not unexpectedly, precipitation is increasing with both time and higher emissions scenarios. So our biggest precipitation increase is 2080 in the high emission scenario, the RCP 8.5. I think the most important conclusion is this second bullet here, is that the difference between our various projection scenarios was not that high. On the low end, 6.9%, on the high end, 9.6%. All of those are large relative to historic conditions, though. So the model or the scenario that gets chosen is not as important in that a scenario gets chosen. So choosing to assume we're going to have low emissions is fine. Choosing to assume we're going to have high emissions is fine. The most important is the acceptance that precipitation is going to change in some way. And as the other groups had, those precipitation changes ranging from 6.9 to 9.6% led to higher runoff volume changes ranging from 8.1 to 14.6%. So small precipitation changes do lead to increased runoff changes. Next slide.
Probably need to wrap up pretty soon.
Perfect timing. That might be our last slide. We had one more, but it just said thank you, I believe. So with that, if there are any questions, I'd be happy to answer them, as would my other group members.
Randy or Alicia, are you guys on?
Yes, this is Randy. How are y'all this afternoon?
Excellent.
Randy. Well, I'd like to thank Greg, Melody, and Hayden for a great job. The final answers or the conclusions, I believe, represent something that is easily conveyed to the general public and to decision makers. When you narrowed it down like that, we can have a lot of statistical information, but again, they're looking for simple explanations and to try to go into the different patterns. I believe the approach that you took was best, again, to convey that, yes, indeed, climate change is real and it's quantifiable, and based on this study, this is what we can expect in the future. So again, I believe you did a great job.
Thank you.
Thanks, Randy. So as we move on to Frederick, I'll just, what's interesting though is that your particular choices in terms of selecting GCMs and RCPs, et cetera, kind of, I think more so than other groups, minimize the variability associated with climate change so that you could make that conclusion that the change that is expected regardless of RCP and regardless of, season and et cetera, is more significant. That's interesting. And I'd like to probe further if we had more time, as to why that was. So what was it about your decisions in picking the GCMs and that sort of minimize the variability associated with climate change? Because I think some of the other groups had a higher degree of variability. And of course, we're all working in the same general region, so geographic region. So that's an interesting area. I mean, we can maybe take that discussion to the Q&A, but let's, thank you for a great presentation. Let's move on to Frederick. Chris and Leslie, you're up.
Okay, so let me, okay, can you all see this?
You're up. Yeah.
Yeah. Okay. Hi, everyone. This is Christopher Barber. I'm with the I'm a environmental engineer with the Philadelphia Water Department in Pennsylvania. My partner on this project is Leslie Munoz from Friesen Nichols in Houston, Texas, and our group was charged with performing a climate study for what we're calling the Pine Avenue, East Church Street, County Lane Triangle, located in Frederick, Maryland. And our partners on this are the Drexel University, the City of Frederick, and the County of Frederick. Okay, as far as the introduction, we have the county is located in kind of the north central portion of Maryland, and with its county seat being the city of Frederick, which is located approximately a little less than 50 miles northwest of the city of Baltimore. The county population is a little more than 240,000 as of the 2010 census. The city has a population of a little more than 65,000, making it the second.
Sorry, there's somebody who's not on mute. If you don't mind, if you're not speaking, if you don't mind going on mute. Sorry, Chris.
Okay. Making the 5,000, making it the second largest populated center in the state of Maryland behind Baltimore. You also have the county area is around 667 square miles, with the city covering about 24 square miles of that, of which 23.95 square miles is land, and about 0.1 is water, or 0.42%, and it's located within the Carroll Creek watershed, which is this area here inside of the blue circle. Okay, as far as the background, we interviewed 3 representatives from the city of Frederick and county of Frederick, Jennifer Williams from the city of Frederick, Rebecca May from the county, and Shelley Strom from the Nelson Institute for Environmental Studies as part of this project to come up with their utility desires, which consisted of MS4 permitting, support for and test current projects for future issues with stormwater, and are the current, and they also wanted to know, are the current capital improvement methods adequate enough. The total site area, they gave us as part of it, the total site area is a little more than 5 acres with 3.39 acres, or roughly 67% of that being impervious surfaces. It consists of single-family residential, light industrial, and institutional uses. Urban land soil type is the predominant soil type, meaning that further, if you want to go into any like further studies in that area, you probably have to do extensive soil testing and everything with that. And as far as the stormwater infrastructure, inlets, there's multiple inlets and pipes located along Pine Avenue and East Church Street. There's no infrastructure on the County Lane side. The site is, this is a map of, showing the site with its, and a layout of, approximate layout of the stormwater pipes and inlets. The green arrows represent the general direction of stormwater runoff to the site, which is, in fact, and the main problem is that stormwater runoff from the stockyards located to the north and from Pine Avenue is causing flooding issues behind the residential properties located towards the southwest side. The main discharge point is on the northeast, is on the southeast side, and it drains to an outfall on the Carroll Creek. As far as our criteria that we used the design storms of 1 year, 10 year, and 100 year, which the city asked for, and 24-hour duration. And then our hydrologic parameters were based on the drainage area from the 2012 DEM to time of concentration from TR55 and stormwater GIS data. The land use determined the curve number. Impervious percentage was determined by land use also. And the main rainfall distribution we used was NRCS type 2, and the IA was following the MDE formula of 200 divided by CN minus 2. Here's another map showing the overall drainage area that's impacting this site. The drainage area is roughly 76 acres. We determined a lag time from the time of concentration of 6 minutes. The CN is, the curve number is 87, the impervious is approximately 70%, and the IA is 0.3. Okay, the climate protections, and for this, to do this study, we had to formulate a virtual rain gauge station based on a mashup of roughly 10 different gauges that were located around the city and county. Most of them were around near the city, and a couple in the northern part of the county. And we needed to do that because we couldn't find a single station that had complete data coverage over the entire baseline period, which the city asked us to extrapolate to 2020 from 1970 instead of just 1971 to 2000. We extrapolated that to 2020 at the city's request. And then finally, this is a table that shows our basically annual seasonal projections and historical data based on that study. This is contained in these two tables. And then as far as methodology, I'm going to turn it over to Leslie to finish.
All right, thank you, Chris. I am going to speed through this, so I apologize in advance, but hopefully we can catch some answers and questions later. So, kind of similar to what the other groups have said, we had a ton of DCFs that we calculated based on the projections and the models we chose and time slices and all that good stuff. So we had all these DCFs and we had to figure out a way to make some sense of them and to select a few that were meaningful and useful for the city. So, and looking at the different scenarios of emissions and looking at the different downscaling approaches, there wasn't something that jumped out. There seemed to be a little more variability for the 8.5 emission scenario than the 4.5, but it wasn't consistent enough through all the months. Something we did notice, however, can you click, Chris, please? Okay. Was that if you look at the medians on the monthly distributions, regardless of the emission scenario, regardless of the downscaling approach, there seem to be these seasonal patterns. So there is a low that happens in October, so that whole distribution for October tends to be lower than the rest and tends to have a median that's negative, or not negative, but that indicates a decrease in rainfall. Whereas the summer and the winter months tend to have medians that are higher than 1, and usually the highest out of the year, indicating that the highest increases would be in the summer and winter months. That being said, there is a ton of variability here with, definitely showing some decrease in precipitation as well as some large, close to 70% increases that are possible based on model results. A note here, as we look at our DCFs, we did have a slightly different calculation of them. So our DCFs are reported as a ratio between our projected rainfall amounts and our historical modeled rainfall amounts. So any number above 1 is an increase, and a number below 1 is a decrease. Next one, please. Okay, so because we noticed a seasonality component to our DCF calculations, we also went back to NOAA Atlas 14, which performed their own seasonality analysis based on the historical data they had. And based on that analysis, we noted that, for something like a storm that's a 2-year storm where it's very frequent, you see that storm tends to happen any time of the year. So there are a lot more storms in the summer, but it happens at any time of the year. But if you get to something less frequent, more intense, like your 100-year, you start seeing that the range of months in which those events happen are really contained between June to September. Same thing with the 50-year, 25-year, and you're going to see that most of those rain events that are the most drastic or the most intense are going to happen in those summer months. Can you click, please? So with that in mind, we chose this period of time, our DCF, to calculate some average values for the summer months specifically. All right, can we move on? Next one. So here are the values. You have to click a few times on this one, Chris. So I just wanted to point out a couple of things. The low end here being a 1.03, meaning a 3% increase, and the high end here being a 21% increase. So you see that there is a moving from that 7.9 existing value for the 100-year to a 9.5 inches for the higher end. Next one. All right, so for our case study, now that we had all these DCFs and precipitation values, as well as the existing and some characteristics of the site, we used HMS to model some hydrographs for here. Click, please. So here are our results. So for peak flows, again, kind of at the low end, the high end, you'll see those values there in terms of summaries, but most interestingly, the percent changes. You see that those increases are fairly close to whatever the percent increase in the DCF was. They're not exactly the same, but they are similar. And we also noticed that as you decreased your frequency, the percent change also seemed to decrease as well. Click, please. Click a few more times. Okay, same pattern for the runoff volumes. So again, very similar percent increases to what the DCF values were applying. Next. So this is a different view of this. So this is a family of hydrographs that were results of our model. So you'll see it's a family for the 1 year, for the 10 year, and for the 100 year. And you obviously have more variability or a bigger range in the 100 year, but all in all, it's about the 21% that we're applying at the highest end of the DCF. Next. So based on those observations, we were curious, what would that mean in terms that we can understand today? And so what we came up realizing is that what we're calling a 2 year today is what our highest end of the 1 year projected value could be. And going all the way to the third line of that table, that means that something close to the 300 year event today is what we would be calling a 100 year in the future. So basically more rain more frequently was the takeaway from this comparison. That being said, I think something that we wanted to point out as well is that, Frederick does use the MDE criteria manual as sort of its baseline for its design purposes. And a lot of the parameters and requirements that are in there are based on specific design storms, frequencies, and depths. And so I think it was important to note that if we're seeing that, more rainfall and more frequent rainfall is going to be expected, these criteria that is listed on the slide probably need to be updated. I guess the other option is not updating it, but that would also come with the realization that the level of protection or the level of service that facilities are designed to is just not going to be the same. There also has an implication with things like inlets and pipes, which are usually designed for more frequent storms, and just having the knowledge that they're probably going to surcharge more frequently or reach their capacity more frequently than is expected. So I believe this is our last slide. So with that, we can take any questions if there's any time for that. So.
Thanks, Leslie. Yeah, we are a little bit behind, but I want to give Shelley, Jennifer, and Rebecca a chance to make any comments if they have any.
Yeah, so I actually really appreciated you comparing that to, what the projected, 1 year would be compared to a current design storm of a 2 year. I really appreciate that. That's very helpful for us, in case, state regulations don't change, we still have something to shoot for, kind of. But just to clarify, so you were saying you weren't seeing the same thing as some other groups as far as your DCF for inches of precipitation versus runoff volumes? Is that correct? You were seeing a similar
percent change?
Yeah.
Yeah, so on our end, I mean, they really stayed very similar. They weren't exactly the same as our DCF percentage, I guess, that we're applying of difference, but they were fairly similar, I mean, within a couple percentage points. So we did not have the same trend as some of the other groups, which was interesting. Now, we also had different software. I don't know if it has anything to do with that. And then we also had, kind of the way that we modeled this, we didn't model the 5 acre site. We followed, we modeled anything that contributed to that point, which was the 70 something acres.
Mm-hmm.
And so I don't know if size also has something to do with it in terms of, maybe 5 CFS is 50% of a half acre site. But 5 CFS, it's not much for a 70 acre site. So,
yeah, true.
So it may dilute some of that because of the size as well. So that's some of the hypotheses there that I have on that. But yeah, you're correct. We didn't really see that trend on our side.
So you're saying more large scale, city overall, we're not going to see that much of a difference, but maybe on smaller scale, like this localized flooding, we might see a bigger impact.
Well, I think on percentage points, I think on absolute like CFS or absolute acre feet, that may be a different story.
Mm-hmm.
But again, 20% of a 70 acre site is more than a 50% of a half acre
Mm-hmm.
site. So it would still be, I think it's still significant. It just doesn't show up that way in the percentage numbers.
Yeah, and then if we have time for one more question, I noticed there's actually a decrease from the 2080s to the 2070s. Did you have any idea why that might be?
On the DCF values, or are you looking at box plots?
I was on the DCF values.
Yeah, I mean, those ended up being, you know, average of the 4 months, and they were different percentiles.
I'm pulling up the front now.
So I don't know. It doesn't. I didn't necessarily see the trend either that between one time plus and the other, like that was the determining factor of like change. So yeah, I don't know just how they shaked out, but it wasn't too far off from the other, so it was fairly in line.
Yeah, I hate to say it, but we're going to have to move on because we're running about 5 minutes late. Yeah. So we can take this to the Q&A. So if you guys want to continue that discussion, please do it in the Q&A. But we should move on to Tacoma Park, and just a note to our participants, we will be running till 6:05, a few minutes late, just because I want to make sure all groups. So if you can bear with us and stay till 6:05, we'd appreciate it. So Cassie, Andrew, and John, you guys are up.
Hi everyone. Hi everyone. My group has worked with the city of Tacoma Park throughout the duration of this course. Tacoma Park is located in Montgomery County, Maryland, and is approximately 2.1 square miles. They have a small population of 17.8 thousand. They are a MS4 jurisdiction, so they have to provide stormwater reports to the state. Tacoma Park currently does not have any specific precipitation models and standards for water quality and stormwater design. They also currently have an extensive existing system that is largely built out with limited new development. Over the past 5 to 10 years, Tacoma Park has been experiencing more frequent flash flood events. These flash floods affect a couple of streets, but so far have caused little to no property damage and do not impede traffic. These events tend to be related to minor obstructions in their stormwater system, so they are of limited concern. They have also been having concerns about erosion near streams. The major concerns that Tacoma Park officials outlined during our talks is managing and maintaining their current infrastructure, identifying their future needs in regards to stormwater management, and the state requirement of treating 20% of existing impervious area. For our first assignment, we downloaded data from Climate Explorer in order to analyze the changes in total annual precipitations, days with more than 1 inch of precipitation, days with more than 2 inches of precipitation, and days with more than 3 inches of precipitation. The baseline for the total annual precipitation is 43.5 inches based on data from 1970 to 2000. Based on the data from Climate Explorers, it can be assumed that even with low emissions, the annual precipitation will increase above the baseline in each period that was examined. These are the charts for the number of days with precipitation above 1 inch and precipitation above 2 inches. The baseline is 5.9 days for precipitation above 1 inch and 0.5 days for precipitation above 2 inches. On average, both of these events should increase above the baseline for low and high emission scenarios. Here you can see the chart for days with precipitation above 3 inches. It has a baseline of 0.1 days and on average shows no change. The Drexel effect should be noted, which is that GCMs underestimate daily precipitation totals by roughly a factor of 2, though they tend to be accurate when simulating annual precipitation.
Thanks, Cassie. After we established the baseline data and predicted changes from Climate Explorer, we broke that down a bit further into the seasonal changes. To do this, we went into the data and characterized each of the data point outputs by their season that they fall into, then took the min, max, and average for each of those. As you can see here, there's some fairly significant ranges in the data. However, all the averages are trending upwards compared to the baseline. As expected though, the RCPs of 8.5 are climbing faster than 4.5, which makes sense with a higher emissions scenario. Also note the fall averages appear to stay pretty consistent compared to the baseline in relation to the other seasons. And as previous groups have mentioned, we are thinking this is because of the hurricane season. Next slide. Once we determined the precipitation change values from Climate Explorer, we moved over to determining the DCFs using the MAPA tool. Shown on the right are the plots of the DCFs for the midterm and the far term, midterm being 2040 to 2069, far term being 2070 to 2099. On the left, we have broken down the max, minimum, and average for each of those. The DCFs that were shown here represent the full range of values that the GCMs produced. The reason that we're doing this is to show the massive range that GCMs produce, and just to show the variability that is associated with this exercise that we went through. This was also requested by the city of Tacoma Park that we show it this way. As you can see from the max, min, and average, the far term range increases as does the average compared to the midterm. Next slide. So after we went in and looked at the DCFs, we started to look a little bit more about the variability between them. With 10 GCMs, 2 data sets, and 2 RCPs, there's obviously a fair amount of data there, and we wanted to make sense of this variability. So here we took the months of January and June for both the near and far term time slices and broke out the different data sets, RCPs, and GCMs. In general, as you can see here, the GCMs have the largest amount of variability. And also note the metadata data set tends to have a little bit higher DCFs in relation, or I guess, versus LibNet data. And lastly, RCP of 8.5 is also higher than RCP 4.5, which lines up with our original results with baseline and predicted precipitation data taken from the Climate Explorer.
Cool. So now we'll talk a little bit about how we selected the DCFs that we're going to be using for our case study modeling exercise. And what our group did was for a high and low scenario, we assumed the max of the max and min of the min DCF for each time slice. Now this is fairly extreme, and you'll see especially compared to other groups, and probably not the most prudent design decision. But as we're seeing, the selection method for this part has varied widely between groups, kind of indicative that we don't have the best methodology down yet for really discerning what is prudent. And to some extent, when we are selecting these GCMs and assuming these are relevant, we went through a whole GCM selection process. It becomes harder to dismiss them as outliers, as we're not really sure which one is the most likely scenario. So I think the real design decisions lie in understanding both the total order of magnitude of your variability. Again, that's the max, min of the min, but also, as many other groups did, where your variability concentrates, right? So with that out of the way, the DCFs that we selected, we applied to 2 sets of design storms. Tacoma Park uses the Maryland Stormwater Manual for design, but we also apply these to Atlas 14 as well, as it's a little more site-specific to Tacoma Park and is based on more recent data. Next slide. Real quick, for our temporal distribution, we used 3rd quartile 50% distribution from Atlas 14. This is standard quartile for a 24-hour storm. Go ahead. Oh, next slide. Oh, perfect. Okay. So for our case study, we were looking at the area of 2nd and Allegheny. This is a low-lying area in the city that has been a source of frequent flooding more recently, especially when there are high-intensity flash storm events. you'll see that the specific site is noted in the smaller circle. But what we tried to do was delineate a larger area that's likely going to contribute runoff to that specific site, as this is a very hilly area that kind of concentrates in the valley at 2nd and Allegheny. To do this, we used EPA's SWIM. We made a very simplified model with no conveyance system, but we did delineate or divide 24 separate sub-catchments with unique slope values, ground covering, etc. So our model is not the best for understanding the conveyance system and peak runoff velocities, but it does, I'm seeing I have 1 minute left, does a fair job of estimating overall runoff potential that could enter the system. Next slide. So modeling results is just a quick note. We did this modeling exercise for 15 design storms. Our 2, 10, and 100-year storms, both baseline and scaled to 2 time slices for a median and high scenario. We removed the low because that it doesn't really add a lot of value for this exercise. And what we were seeing was really driving increases in runoff was the selection of a high scenario, which was based on our upper GCMs, which is indicative of the GCM selection really driving how you assess your upper bounds. So next slide. Cool. So to conclude, general recommendations from the group to the city or in general, based on the variability we're seeing and potential for change, redevelopment of design storms is going to be critical. And these design storm adjustments should be incorporated into a larger, more robust model in order to understand more localized or areas that are flying under the radar right now, but might become significant problems in the face of climate change in the future. Just a last note that what we've selected as the DCFs or GCMs are not the only possible climate change outcome for this area. So I think it's really important to remember that this work maybe doesn't necessarily need to drive specific design changes, but should be used to foster a conversation between regulators, customers, and the rest of the shareholders of the community to understand what potential changes climate change will pose for them, and how that collective of shareholders can work together to mitigate the impacts of climate change. Next slide. Cool. Questions?
Thank you, John.
Oh, hi, Lee.
Yeah. Did you find the same difference between the DC, the percentage of increase in precipitation and the runoff as the other groups did? Like the runoff
no.
is more, like a more percentage is applicable to the runoff than the precipitation.
Yes, we were seeing, as some of other groups, maybe not to the same extent between the design storms, but in general, the DCF was not a direct relation to the increase in runoff. So there's some variability or uncertainty there based on evaporation or infiltration into the ground, right? Yeah, there's a quick answer. I can talk more offline in detail about that.
Right. There was another question, a point that was made earlier with regard to another presentation, that there is a seasonal variation in the precipitation and in the runoff amount due to, lack of, due to the, like in the winter, you don't have enough leaves or foliage. So that could be a contributing factor to that.
Yes, that was not considered the modeling assumptions, we did not vary based on season, but that definitely could have an impact in the overall runoff. So it was outside the scope of our model, but we can explore that more or talk more with you about it. Yes.
Thank you. That's great. Good work.
You know, another interesting piece of what you guys did is you picked the min of min and the max of max. So, you know, I just wanted to sort of underscore that's a different direction that you could go. I mean, you've got all this uncertainty. So some of the groups try to, you know, find a slam dunk, like if I shoot for this, no matter what, I will get a benefit, but I'm not covering the worst case scenario, but I might say, I'm not going to cover that now, I'll worry about that later. You guys tried to, I mean, others tried to average out the variability, and you guys tried to represent the extremes. And I just think that that's a really interesting sort of range of perspectives on how to deal with the problem that we're talking about here.
Yeah, I think to that point, part of, I think what the design answer is that you need to understand that, you know, upper bounds worst case, and then your realistic upper bounds, and understand the incremental benefits from increased infrastructure that you're gaining, and what level of risk you want to accept based on the uncertainty between a realistic upper bounds and a worst case upper bounds.
Yep. Okay, so with that, we are about 5 minutes over, but I think I want to just thank all of the students. I think, you know, all of the material that we covered, to do it with only 5 minutes delay is remarkable. And I thought the presentations were really, really amazing. We covered a lot of ground in this course. It was new material to a lot of us. There is no textbook on how to do this, so we were figuring it out as we went ahead. And so I just want to congratulate you on these presentations, and thank also the government partners for being good sports about this and dedicating your staff time to work with us on this. And you will be getting final reports from each group in the next week or so, once I grade them. And we look forward to sort of ongoing conversation with you and with any of the students. So some of the students have indicated an interest in consolidating some of this information into a paper. Fatima, who's been an amazing TA, may also be part of putting that together. And so I just want to thank everyone for their work here. And special thanks also to Corinne for handling all the logistics, both with this webinar and with the interactions between our team and the various agencies. So with that, thanks all. Class students, if you want to go to our usual Zoom link, we can have a short debrief there. But just to everybody else, join us next beginning of October. Our next Green Infrastructure, Climate, and Cities webinar will be focusing on approaches that Boston, Pittsburgh, New York, and Philadelphia are taking for collaboration between cities and universities on addressing the climate crisis. So please join us next month. And with that, have a good evening. Thank you.